Hello, everybody. Welcome to this afternoon talk. My name is Sid Choudhury, and I have here Karthik with me. We are both from YugaByte. We are an open source distributed SQL database built for the modern cloud native era so that you can run it in public cloud VMs as well as containerized Kubernetes-based architectures. With that, I will get started, and then I'll bring on Karthik in the middle of the talk to take us through the remaining part.
Yeah.
Thanks, Karthik.
Thank you.
So let's get started with a little bit of orientation so that we know what space are we talking about. There are two types of data stores in the extreme. One is called an analytics store, or the common term is an OLAP store. The other extreme is an OLTP store, or a transactional store. There are distinct access patterns that each one of these stores are built for. If we take the OLAP side, then the data gets sort of written to that data store once, let's say every night. Then it is read many ways, again and again. It has got few concurrent sessions because it's about users, human beings talking to it through a live ad hoc analytics style UI, and you're analyzing petabyte scale data to get some insights. It's actually exactly the opposite on the other side, where a transactional database has to account for writes and reads happening at the same instance of the time. The data you are trying to pull out is also being written by somebody else. So chances of you getting incorrect are very high. So that's why transactional databases ensure that you get the correct answer all the time, right? Many concurrent sessions, because it's not about human beings anymore, it's about your application code that is deployed probably in IoT devices, which will be in millions. They're all talking to your database at the end of the day. And the queries that you're going to run, they need to come back really fast. Typically, single-digit millisecond query latency is sort of the state of the art, if you would say, in transactional databases. So the type of data is point reads and short-range scans, as opposed to full table scans, which is sort of the standard in our OLAP space. And data storage is typically in terabyte scale. It used to be in gigabyte scale. I would say 10 odd years back. We are today in terabyte scale. If data continues to explode, these things will change. Petabyte will become exabyte. Terabyte will become petabyte in no time. If you have not guessed it, this talk's focus is on the OLTP side of the house. We're not going to look at the OLAP side of the house. Some examples to drive home the point. There are, by the way, each one of them have a NoSQL flavor of what kind of client language you talk to the data store with. And there is an SQL flavor, which is commonly known as structured query language. All of us learn, most likely as engineers. Most of us learn that in school. And in the OLAP side, there are a lot of players. And here are some examples to sort of drive your thinking about who they are. On the OLTP side, there are also lots of players in both NoSQL and SQL categories. For this talk, we're going to focus on OLTP SQL database. Okay? I know many of you are thinking, it's a solved problem. What's the big deal? We've been using MySQL, Postgres SQL, and Oracle for ages. Why change? I will prove it to you that we need to change. So let's start with why, as developers, we love SQL. Okay? First is about the flexibility of writing the queries. SQL is about modeling your data once in some sort of a normalized manner, laying down the data in terms of tables, and then writing queries on day one, changing queries on day two, and changing queries on day n as our business needs change. This is different than NoSQL. NoSQL, you model your query first, and then if you need to change, it's a hard problem, because your data is already laid with respect to the query you want to solve. SQL is very powerful about query flexibility. And also query flexibility goes hand in hand with modeling richness, performance. If you have lots of joins, lots of foreign key constraints built into your SQL queries, irrespective of whether it is A single node SQL or a distributed SQL does not matter. It's going to take more time for the database to give you the answer back because it is going to do more work on your behalf, right? But the power is in your hands as developer to choose how you want to do your modeling, okay? And that's the kind of response you should expect from the database. Secondly, SQL is about rich ecosystems. Almost everything that is SQL-based has a very rich ecosystem of integrations, developer tools, IDEs, visualization tech. It's all about very easy to get started. You can probably build your own integration faster if the database that you're talking to is a SQL database, okay? Last but not the least, as we saw in the big data wave and now we're seeing in the cloud native wave, SQL is the universal data access language. We all have learned it once, and the beauty is that we can use it forever. Once you have learned SQL, it's like learning how to ride a bike. You don't forget it, okay? Now, wish it were all positives. Unfortunately, there is always something wrong with all these technologies. Why do devs hate SQL? First is, most SQL databases that we're aware of, Postgres, MySQL, Oracle, SQL Server, they're all monolithic databases. There is only one node that can accept your incoming write request. And if you are serving a high volume application, which is what more or less the internet era has allowed us to do, take IoT, take retail, take fintech, all these are high volume applications because millions of users are touching them at any given point of time. Your SQL database is in deep trouble because it does not have the compute capacities to serve those incoming write requests. So what do as engineers do? We start figuring out how to solve this problem. There are two ways. One is what is known as sharded SQL. We create n independent instances of SQL databases and let our application manage which record or row is present in which database instance. Remember, each of those instances don't know anything about each other. So it's all the application's responsibility. Secondly, we augment our SQL database with some NoSQL. But NoSQL predominantly is a non-transactional technology. Most of them, you cannot even read the write that you have just written into the database, given how eventual consistency and lack of ACID work in NoSQL databases. So you're limited as to what exactly can you do. And immediately, as a developer, you have started compromising. You hate what is going on. Not a happy experience. Secondly, it's about handling infrastructure failures. As we move to the cloud from private data centers, infrastructure, which is disk, node, availability zones, regions, and entire clouds, they're all prone to failure. Because by design, the way the cloud works, it's massively shared infrastructure that the cloud providers have created for us on commodity hardware that we all get to use on a utility basis. Very different than private data centers where we had our own racks, our own dedicated networking, and our specialized big boxes that we bought from IBM, Dell, and HP. Okay, in that world, the infrastructure is going to fail absolutely, and SQL databases are very bad when it comes to handling failures. So as engineers, we have to now deploy replication schemes and manual failover technologies to make sure that we can handle those failures. Again, unpleasant experience. Last but not the least, as we are all building, as we are trying to draw the maximum out of the cloud infrastructure that we are using, whether it be Amazon, Google Cloud, or Azure, we want to start building what is known as geo-distributed applications to make our applications live closer to where our users are, and not just have a single region application where all requests across the globe come in to be served. In that world, your SQL database is again another bottleneck. You can scale your application out to multiple regions, but your SQL database has to sit in a single region on a single instance, and you have to serve everything from there. This is where it gets challenging. So that's why we are here to talk to you about distributed SQL. Simply put, distributed SQL is about keeping all the things we love about SQL and removing everything we hate about it. What does it mean? It means keeping the SQL features intact, which makes, as developers, happy, right? And then the horizontal write scalability, fault tolerance, and globally consistent writes are the three things that I talked about that are bad with monolithic SQL. Lastly, you must be thinking, I just distributed my data. That means if I ask a query, the query will get distributed, and as a result, it'll cost me more time and latency in order to serve the request. Now, if your application is architected in such a way that majority of the time you're actually doing point lookups and short-range scans, which is what the OLTP workload is, then you can serve it from a single instance most of the time. Some different instance depending on the query, but each request will hit only one instance. And at that time, you want to ensure that instance is able to serve you the correct data without talking to anybody else. And that's where the low read latency aspect kicks in. So with these 5 things, let's talk about the two dominant architecture schools of thought that have come by in the last 4 or 5 years, and sort of compare how they deliver these benefits to us. So first is Amazon Aurora. The way Amazon describes it is a highly available MySQL and PostgreSQL compatible relational database service. It was made generally available in 2015. It is Amazon's fastest ever growing service. Not just fastest ever growing database service, fastest ever growing service. So clearly, as engineers, we love something that our Aurora has to deliver. Okay? It's one. Secondly, Google being Google, Google is not going to leave itself behind. Google has another, it's considered an engineering marvel in its own right, and that's called Google Spanner. And the tagline from Google is the first horizontally scalable, strongly consistent relational database service. Okay? Google has been using it internally for more than a decade, but Google Cloud started offering it as a managed service starting 2017. Right? And if you see, one of them is based on shared storage architecture paradigm, and the other one is based on a shared nothing architecture paradigm. And that's what I'm going to talk to you about, how each of these architecture paradigm maps to the 5 desired properties we want out of our distributed SQL databases. Let's dive right in. First is SQL features. Depth of SQL support. Amazon Aurora is fully MySQL and PostgreSQL compatible. So whatever you were doing before on MySQL and PostgreSQL, you can do all of that with Amazon Aurora. It's not the case with Google Spanner. Google Spanner uses a subset of SQL feature, or exposes a subset of SQL features, and it's not actually standard with any of the existing open source SQL databases. It's its own flavor. And importantly, it actually does not support things like foreign keys. So it puts a little bit of restriction on the kind of SQL applications you can write. Okay? So we can say that the SQL support is a little bit limiting in Google Spanner. But nevertheless, it's still SQL. You can still do your transactions, you can still do your joins, and so on. Let's go into the next one, horizontal write scalability. Now, this is how Amazon Aurora looks underneath the covers. It's actually a single node SQL running on a multi-zone distributed storage engine. What do I mean by that? You see at the top, those are the SQL query layers. There is one master in the entire cluster, which is responsible for taking your writes and serving you correct reads. And there are a bunch of replicas marked by R in there. You can talk to the Rs to get some stale reads, but you can never write to an R, okay? Because it's a read replica at the end of the day. Underneath, the storage layer is highly available, replicated across multiple zones inside a single region. Now, the benefit of this is that we can add as many read replicas we want in order to scale our reads. If we have a heavily read-intensive application, then this is not a bad idea. However, if you have a write-intensive application, you're in trouble, because you cannot add more primary instances. Okay? That's one of the core limitations of the Aurora architecture. Spanner, on the other hand, takes this problem head-on. It says that when you give me any SQL table, I'm going to divide into small chunks. And let's say this is a 3-node cluster. I'm going to put 1/3 of the chunk in instance 1, 1/3 is instance 2, and 1/3 in instance 3. The power of this model is that as I can add as many new instances as I want, and Spanner will automatically balance the data in the new node. So if I added one more node, it'll become 1/4, 1/4, 1/4, 1/4. Okay? That allows me to actually do both the things. I can add primary instances. I can add read replicas out, which are not even shown in this cluster diagram. So from a write-intensive application standpoint, Spanner is ahead of Aurora, okay? Because it provides horizontal write scalability. Third point, fault tolerance. As I said, infrastructure is bound to fail. Applications and databases have to own the problem, have to be architected for handling that. In Amazon Aurora, the failover is automatic, and this is where it shines above your standard relational database like Postgres and MySQL. So native failover and repair, because the moment the M, so if an R dies, no problems, right? I have plenty of Rs lying around. But if the M dies, between the remaining Rs, there is something, a notion of an election, they vote, and one of them becomes an M automatically, right? There is a slight delay in how fast that new M can be created, but nevertheless, as an operator, you are not intervening in that equation. And that means that as an application, I have high availability when my primary instance fails, and obviously I have high availability when my replica fails, read replica fails. Okay? So Aurora is good when it comes to fault tolerance. Spanner, very similar. What Spanner does is, the moment any one node's disk, node, zone, or any of those things fail, new leaders are elected for all the chunks that were lost in the remaining existing instances. So the net effect is same. It's just that in Spanner, the leader election is actually much faster compared to what you would have had in Aurora, because it is happening at a smaller granularity compared to the entire instance level. So now, if I were previously writing row 1 on instance 1, after the failover, which is automatic, I will write to wherever row 1 is now leaded at, which let's say happens to be in the second instance. I will write it there. So from an application standpoint, it's great because I now can write to it as if nothing has happened. Okay? So both of them are equal at a high level when it comes to this. Then it gets very interesting. Now we're talking about multi-region geo-distributed applications. And we want global consistency. I'll explain why global consistency is important. So in case of Aurora, if you want to deploy it in a multi-region deployment, then you will have what is known as a multi-master configuration. Full copy of the data in one region, full copy of data in another region. They both take writes for the entire data set. And that itself is a problem, because the moment you do that, you have to resolve conflicts if the same key has been updated on two sides. The example is here. I'm just changing my balance, deducting $10 from balance on one side and deducting $100 of balance on the other side. In a globally consistent database, it doesn't matter which one went first. I want my balance to be deducted from $110 at the end of the day. In this one, if balance minus 100 goes first, then that means balance minus 10 goes later, and that's the last writer wins, which means that we actually lost out on $100 balance. And if it's the other way around, we lost out on $10 of balance. So it's easy to build inconsistent and incorrect applications if you deploy Aurora in a geo-distributed setting. That problem is not possible in Spanner. Because Spanner is architected, remember, Spanner was built in late 2010s to solve the Google AdWords problem, where multiple different marketing managers are decrementing their ad credits across the globe. So this is the core foundation of Spanner, where irrespective of where the write is coming from, it will be globally consistent. So in this case, I can just talk to my local data center, right? Both of them are talking to the local data center. But when this region 3 sees that the balance key is getting updated, it will automatically send it transparently to the application to the right place, and that instance will then serialize them. So the net result will be balance minus 110 as the new balance. Completely transparent to the application. You don't have to do anything. Okay? Finally, this is the last section for my low read latency. Now, in case of Aurora, low read latency is given because there is only one place where writes are being taken. So if I want correct reads, I should just ask that master, and it will serve me immediately without looking at anybody else. Because technically, remember, the SQL layer is not a distributed system. The distributed system is underneath in the storage layer. In Spanner, there are distributed systems at the upper half, and there is a distributed system at the lower half. And now, in a traditional NoSQL database, if you want any kind of better, more consistent read, more correct read, you have to do something called as a quorum. I have to go and talk to my replicas to see, hey, what values did you see last? And then I have to figure out what was the latest timestamp and then serve that. In the Spanner architecture, that problem is avoided by ensuring that each instance posts the leaders for a certain set of shards, and the moment I ask the value for a given key, Spanner will automatically route it to the instance where that key is leadered, and you'll get the correct read immediately without talking to anybody else. Again, very powerful in a OLTP database, which has where lots of reads need to be served. Typically, reads are significantly higher, probably 5 to 10x higher than how many writes are served in any of the applications we use today that we have come to love. Take Netflix, take Uber, take Airbnb. The read volume is much, much higher than your write volume. Okay? With that, I have completed the comparison between Aurora and Spanner. Want to leave you with this thought that in the battle of this architecture, Spanner actually beats Aurora because it is more general purpose and allows with the notion that there is no performance and availability bottleneck built into the system. You can actually scale as wide as you want and tolerate failures much more cleanly than you would in an Aurora-style architecture. Secondly, Spanner is built ground up for geo-distributed applications. And that essentially future-proofs your database from ever falling apart as your business grows into a global business. You may be starting today in a single region setting, but if all of us are successful, then it'll grow really fast. Users will come from all across the globe, and you will not be able to really use the cloud's multi-region capabilities if your database is not good enough. However, Spanner is more complex to engineer. It's a harder technology to build because of all the things that are going on in the background. It specifically needs something called as clock skew tracking, and that's what Karthik is going to talk us through as to how Spanner and some of the open source derivatives, YugaByte DB being one of us, deal with this kind of a problem. Karthik?
All right, thanks, Sid. All right, hey guys, I hope everybody's not sleeping because we're going to go into a little bit more detail, but we'll try to keep it light and crack a couple of jokes where appropriate and so on and so forth. Okay, so to summarize, we talked about Spanner and Aurora, and we said Spanner ensures you is more future-proof, so it's a database built for the future. Aurora is to simplify your operations today, right? That's the head-to-head. And we talked about some of the key things in Spanner, how it does write scalability and geo-distribution and so on. So let's look at the open source derivatives of Spanner. First question, why do I care about this? Well, you may be running on AWS. There's no Spanner in AWS, so what do you do then, right? So there's a number of places where having an open source cloud-neutral database is actually useful. You may want to run this inside containers, inside your company, because you're adopting containers in a big way, Kubernetes, so on and so forth. So let's move forward. So there are a number, believe it or not, of open source databases that are like Google Spanner. So there's YugaByte DB, which we are working on, and there's CockroachDB and TiDB. So these are three of the open source databases that are SQL databases, distributed SQL databases, built along the lines of Google Spanner. So if there's so much of distributed SQL databases going around, how do you analyze between these, right? So that's what we're going to look at. Okay, so since we're building YugaByte DB, we're pretty confident talking about it. The principles from what we know with the rest of the databases are quite similar. So you can kind of put it together in the form of what are some of the things you need to look at to analyze databases. But let's just take YugaByte DB and draw parallels to the others. But it's quite similar how you would try and analyze these Spanner derivatives. Okay, what were the design principles behind YugaByte? And again, once again, all of this extends to the other databases as well. It's consistent and partition tolerant in the famous CAP theorem. NoSQL databases gave up consistency for availability. So CAP, consistency, availability, and partition tolerance. These databases choose CP. But they still give you high availability because they replace any failure in a matter of seconds. And modern applications can experience that sort of downtime for reasons other than the database, like your internet connectivity, your other application servers, so on and so forth. They all have ACID transactions, single row and multi-row transactions. They can do a variety of different isolation levels. If folks are interested, please drop by the office hours. I don't want to put everybody to sleep. And high performance is a core target for us because in the cloud, you need to be serving with low latencies. It is a top order concern in the cloud because the cloud environment is necessarily commodity and noisy. And finally, the aim for all of these open source databases is to be able to run anywhere, like Google Spanner, only on Google, only a managed service, right? There's a number of cases when a managed service may not be as advantageous as it sounds because, hey, I have a networking issue, I have a machine issue. Sorry, you can't see the machines because it's managed, right? And how about you open a service ticket and the people will get back, but God knows when that is, but you really have to do something, but there's nothing you can do. Okay, so at a very high level, these are the three big block diagrams that YugaByte is built to solve. There is YSQL, which converts your traditional Postgres SQL into a distributed SQL query layer. So it deals with the query aspect of the database. There is a distributed document store that forms the core storage layer of the database. And there is a piece that lets it run on any hardware, whether you're talking about containers, bare metal, VMs, Kubernetes, whatever it is, right? So it abstracts out the IaaS. So these are the three top-level block diagrams inside the database. And so where does that put us? So now that we've gotten an overview of how this architecture works, let's look specifically at a few aspects of the database of YugaByte and compare it with the other open source Spanner derivatives, just so you get an idea of how these things work. So the things we're going to look at are SQL features, We're going to look at replication protocol, clock skew tracking that Sid talked about, and the transaction manager, how that happens, okay? And then we're just going to throw something in a miscellaneous bucket where there could be various things that some databases support, some don't. You just have to look at those yourself. The first thing before we get started is cost. Open source databases are free, which makes it a very attractive price, whereas Google Spanner is not. And it doesn't matter whether it's your test data, dev data, you're playing with it, or you're actually running it in production, it's all the same. So, well, that's there. But anyways, that out of the way, let's go to SQL compatibility. So one of the other things that Sid talked about is Aurora is so popular because it is fully compatible with MySQL and Postgres, while Google Spanner is not, right? So what did the open source folks do? Well, what we did at YugaByte was we took the Postgres query engine and we taught it to talk to a distributed SQL data store. So on the left, you have a traditional single node Postgres that talks to like a disk on one node. And the green portion is the actual query engine of Postgres. We kind of changed the query engine of Postgres and converted it to a stateless Postgres and got that to run on top of a distributed SQL database. So what does that mean? It means we have a Spanner-like architectural core, but it is fully Postgres compatible, right? So we're trying to bring the best of Aurora and Spanner as our, and here are some of the things that we support inside the database. So most anything you expect from Postgres, you should be able to expect from us. It may just be a point in our journey, whether we support it today or it's going to be there in a few months. But effectively, most of the common things that you would expect from SQL databases. So how do the other open source databases fare? They do pretty well too. CockroachDB is Postgres compliant and TiDB is MySQL compliant. So everyone made the right choice in trying to make it simple for people to adopt, right? All right, so let's look at replication. Now, how do you ensure, so machines fail in the cloud, right? How do you ensure that your data is still available? Well, you have to replicate it somewhere. Now, if I write data on more than one machine, how do I know that if when my primary machine dies, that the data is actually consistent, right? If you're doing a master-slave, you're definitely going to lose some data. How do you ensure that the data is consistent? That's where replication protocols kick in. Okay, so once again, what do we do with YugaByte? We take a table, that's what the thing looks like in the left, your entire table, and then we shard it into small pieces, okay? So think of a shard as automatically partitioning your table into small sets of data. So we group rows into smaller sets and put them according to some strategy. Now, we take each of these shards and we put them across multiple nodes. So every piece of data being written to a row gets distributed across nodes, right? And the real trick is how do you do it in a way where there's no inconsistency and you don't lose data? And that's where something like a Raft consensus algorithm comes in. There's a number of different ways you can implement consensus, but Raft is one of the easiest and most expressive. And one of the additional features Raft gives you is you can actually change the set of nodes dynamically, which means I can be writing to these 3 nodes, and I can add a 4th node and remove 1 node. So what's the implication of that? Well, you can start with machine type 1, your database running on machine type 1. You have 5 nodes, and after by adding and removing nodes, you could be running on 5 nodes of machine type 2 or in a different zone. So that means you don't have to shut down all your database machines and you tell somebody, this is a notice for downtime of the database. Please don't expect a service downtime. None of that stuff. It just keeps running all the time, right? So it's useful that way. And this is how, at a very high level, Raft works. It looks like every other quorum system, but there is a difference in how the internals work. Once again, office hours would be a great time to talk about it, not going into the details. Writes go to a leader and are written to a majority. So you're replicating it 3 ways, but you're waiting for at least 2 guys to write your data. And all your reads are handled directly at the leader. So that means if you're geographically distributed, but you go to the leader, which is in your geography, you will get very low latency response. So that talks about the low latency reads that you get. So what do the others do? Well, no points for guessing. Everybody uses Raft because it's really simple. Google Spanner started before Raft was a thing. So it uses a family of algorithms called Paxos. Paxos is also a legitimate consensus algorithm, except it's very, very hard to understand. And that should be pretty evident by the fact that Paxos came out, and then there's actually a paper called Paxos Made Simple, And then there's another paper called Paxos Made Very Simple, and I'm sure there's another one called Very, Very Simple, and so on. So it's just a series of papers, and you know what? They finally decided it wasn't simple enough, and people just created Raft and said, this is really simple. So that's what's going on here. Okay, so we're going to take the next thing together because they're kind of related. How do you do transactions and clock skew tracking? Okay, it's just an interesting topic in itself. What is a transaction and why do you care about multi-shard or distributed transactions? Well, I want to update two keys, right? Take the example that Sid showed where you wanted to subtract $10 from your account, right? And you wanted to send it to somebody else's account. So key one is subtract $10 from my account. And key two is, say, add $10 to Sid's account. That's how I transfer money, right? You want to do that transactionally. We don't want me losing the money or him getting the money without and the bank losing the money. So both of those are bad scenarios. So this has to happen atomically. It either happens or it doesn't. There can be no, like it's kind of written, sort of written, or one side written, none of that stuff, right? So key one and key two may belong to different shards. So they could live on different nodes, right? And they could live on different geographies. It doesn't matter. So each of these shards are replicated across nodes. So they belong to different Raft groups. So the picture starts looking like this. You need to write the data to one Raft group, which keeps all the data replicated. And you need to write key two to another Raft group, which keeps all the data replicated, right? OK, big deal. What's so hard about this? Well, the problem comes when you say that the data should actually be written at the same time. So if I'm a user and I keep issuing select my balances for key one and key two, or read key one and key two all the time in a loop, I should see at one instant that key one and key two are some old value, and the next instant they both are the new value, irrespective of what failure happens where. OK, so the hard question, right, is how do you get nodes to agree on time? OK, seems relatively trivial, just use the clock, but it doesn't work. If you use physical clocks, they don't quite agree. So you would need an atomic clock, right? And this is what famously Google Spanner does. They have a true time service, which is powered by a GPS synchronized atomic clock, right? If it sounds fancy, that's because it is, right? So it's really hard to do that. So it is a globally synchronized clock with tight error bounds, right? OK, so if people told you, like, you know what, why don't you just add an atomic clock or two and you'll have all of this stuff? Well, not quite going to happen that way. Most of the clocks that the rest of us poor people have are unsynchronized clocks. They are synchronized, but the upper bound is really high. So that means that you'll get your upper bound at 150 or 200 milliseconds. Now, would you like every single read and write to take that long? Probably not. So you either have an atomic clock or this. Is there another option, right? So there is another option. Turns out it's a heck of a lot more complicated, right? So, but you know, that's what we do anyway. So you know, it's and we call it fun too. So, so it's called hybrid logical clocks. Okay, so you take the physical time on these machines, which is coarsely synchronized with that huge upper bound error limit, and within that time, you start doing causal tracking. Use a logical clock in between, right? So A happens before B, C happens after B. You need to know that within that time. Right? So you do this by using a physical and logical tuple, right? The physical component coarsely synchronized using NTP, and the logical component being a monotonic counter to track causal chains. Now, every exchange between the nodes keeps updating physical time and keeps updating this hybrid logical time, so nodes in a cluster keep normalizing time within themselves. But that still leaves you with some cases when you really can't tell. There were two updates to two different nodes that didn't exchange any conversation with each other, right? Now, in those cases are when you detect what is called a conflict, right? So you're updating a key here and you're updating a related key on the other node, and you're trying to do that at different physical times, but they're within your synchronization window and you don't know how close they are. So what most of these databases do, what YugaByte does, is it really reduces the number of times you would conflict, right? So it doesn't rely on conflicts. It tries to avoid conflicts. But if there is a necessity for detecting a conflict, it tries to maintain correctness over like speed, right? Because we all don't mind if the transaction takes a little longer, but no one wants to lose their money, right? So, OK, so yeah, so what do we do? Google Spanner uses TrueTime, their own satellites and stuff. But YugaByte and CockroachDB use hybrid logical clock with a max clock skew, right? They say that your clock skew cannot exceed some bound, and as long as that property holds, we'll keep doing better and better with most of your transactions. You may never hit in your application a case when there is actually a conflict, but if you do, we'll detect it and restart the transaction or let you know that there's something that's really off and you have to retry that transaction. TiDB goes a different way. TiDB puts a centralized timestamp oracle to issue time. That means everything happening on the distributed cluster has to go to this centralized node in order to get time. Since time is issued by a centralized entity, which is a highly available entity, but it is a central entity, you won't go wrong with clock skew tracking. Now, different products optimize for different use cases, so I wouldn't say one is right or wrong. The downside of going with a centralized timestamp engine is that it won't work well for geo-distributed use cases. Everybody has to keep going back to the central thing. The downside of using the hybrid logical clock plus max skew is what happens if your max skew is exceeded, or how much do you need to wait if you detect conflict? So those kind of issues start coming up, right? So those, well, the other thing is that in all the other designs, you are necessarily scaled out, so horizontally scalable, whereas in this case, the timestamp issuing authority is a single authority, right? So, okay, so there's a miscellaneous bucket. Of course, we know more about YugaByte, so we're going to point out a point. There may be many points to the converse. So things like tunable read latency is something that YugaByte supports. Tunable read latency is the ability to read from a follower node. Google Spanner supports that. YugaByte supports that. Cockroach does not, we believe. Yeah, and TiDB, for example, also does not, but I'm sure there are other features that other folks support that we don't. But the point here is, please do the research on the exact set of features. These are miscellaneous features. It depends really on exactly what your application is trying to do. And finally, there are these set of tests called Jepsen tests. For those of you that follow databases, it is kind of considered like the best in class to figure out whether a database is correct or not. And the way it's done is a number of failures are induced on a database, partitions, node deaths, all sorts of crazy things. It's like the guy really takes pride in breaking it. So Kyle, the person who does the test, and he's really good at it too. So, he subjects these databases to all kinds of imaginable failure conditions that you would think, like, read something, pause the node, try to write somewhere else, fail this node, introduce a partition, read from this other guy, all of that stuff. So Spanner obviously didn't need to do it. They've managed to, deal with their own ads folks, and ads is a pretty big business for Google. If you're thinking Google search, that's their primary bread and butter. If they've kept the people happy, I think it's kind of fair to say it's consistent. So they do really well on the consistency in the face of failures front, but they don't need to run it through Jepsen. However, YugaByte and CockroachDB, YugaByte, we recently ran it through Jepsen, and he was able to verify that for all the claims that we make, the database is indeed correct. So has Cockroach, and TiDB has not. I'm sure they've done a bunch of testing on their own, but this is something like, hopefully in the future they will. But this is another thing to look at, because the question often comes up, how can I trust a small company or a new project? Doesn't it take 10 years or 15 years to build a database? So the way to do that is actually test in a very accelerated fashion with all the errors, so that probabilistically you will not encounter those errors in production when you're running it. If you like this type of content, there's a whole bunch of stuff we write. Please follow our blogs. I think that's it.
Does YugaByte determine algorithmically the partitioning schema, or is that configured by the user?
There's a little bit of control for the user, but YugaByte algorithmically determines that. There's always, with expressing intent, you can do a lot better in the database. So there are schemes to express your intent. If not, it will default to a particular partition scheme. The partition scheme we support by default right now is we hash partition the primary keys, and we are working on support for range partitioning or in order, and you'll be able to choose which one you want to do. And that really depends on your app and your access pattern. Oh, yeah, yes, yeah, go for it, yeah.
So
I thought you were always the first one. Go for it, yeah.
I always get one in. Google Spanner is expensive, but they do handle the operations. What are kind of the worst case scenarios for this family of databases if we're running them ourselves? For example, maybe some region goes down and there's some thundering herd recovery problem that happens.
Yeah, great question. So In the case that most of these databases are meant to be resilient, in order to deploy them, you would have to pick a replication factor and a certain deployment topology in order to survive a certain type of failures. As long as the failures are within the configured bounds, you will have to do nothing extra, and the database will run. So that means you don't have to wake up at 3 a.m. to rescue. You can come at 10 a.m. after you've had your coffee and actually figure out what to do to rescue it by adding nodes and so on and so forth. If the failure bounds are outside what has been configured, then obviously it's a catastrophic failure. In that case, you would rely on backups and other ways to restore it, or that actually becomes a 3 a.m. call. So